Okay, Steve, can you confirm you can see my screen?
Yes, I can see your screen.
Okay, sounds good. Okay, the very last topic, everybody, we have finally made it to the end. We are now going to talk about safety. And not surprising, this is actually one of the longer sections of your ham radio training. And for good reason. Ham radio is a lot of fun, but there's a lot of things associated with it that you got to be careful about. Steve has already mentioned several of those, and they've come up in other topics, but we're going to talk about them. And there are questions, of course, on the exam regarding this. And the good news is much of this is really common sense. If you kind of look into a lot of these questions, the way that they are worded and the way that they're presented, if you kind of take the approach of being very conservative, being very safety conscious, you'll probably do okay. But Steve and Bill and everybody else, if you do have questions, feel free to chime in. This is a really good topic for a little bit of group discussion. So anyway, good ways to guard against electrical shock at your station. Use 3-wire cords and plugs for all of your AC equipment. You want to make sure that your equipment has a good ground. Connect all your AC powered equipment to a common safety ground. And we're going to talk about safety grounds a little bit later. We've touched on them, but making sure your equipment is properly grounded is a big, big deal in ham radio. And install mechanical interlocks and high voltage circuits. Now that is, wow, that was a mouthful there. A mechanical interlock in a high voltage circuit is a device that will turn off power automatically. For instance, if you open up a cabinet, something of that sort. Now, for many of us, that doesn't apply right away. But especially when you were talking about old high powered equipment that uses tubes and everything, that was a very big deal. So anyway, all of these choices that I just talked about there are correct. Now let's talk a little bit about one thing, and that is a ground fault receptacle. Everybody has probably seen them. You'll see these in your kitchen. You'll see them in your bathroom. And the reason being is that they are very important to have any place in your home that is near water. But also, it is also important to have anything like this associated with having a proper ground, like a ham radio station. And I got to admit, I got to make a confession right now. I do not have a ground fault receptacle hooked up to my station. It was one of my winter projects for this year. I had set up my station in a loft in my house, and I said to myself, one of the first things I'm going to do is go and put in what is commonly referred to as a GFCI or a GFI receptacle, and I have not got around to it. But when you all are setting up your ham station, I do highly recommend this. And how these devices work, by the way, because like I said, you've probably seen them in your home. There's a terrific diagram over here to the right that describes how it works. On the hot lead of your circuit, what it does is it measures the difference between the power that comes out to, say, an appliance or something like that compared to what goes in. Now, we talked about before when we were talking about basic circuits with electricity, what goes in must come back out. And truthful, that is true, but there is a caveat to that, is that if you do have a faulty ground, or for instance, if something comes exposed to water and it finds another conductive path, you can have what is referred to as a leakage. And a leakage is a very bad thing. That is where people get shocked or electrocuted and the like. And what a ground fault receptacle does is it detects that. Unless the power coming in and the power going out are identical, what it'll do is it'll shut the circuit off very, very quickly, very abruptly. These have been around for a long time, and I can genuinely say these have saved a lot of lives. They're a wonderful, wonderful thing, and you'll find them in every single home. Now we talked a little bit about grounding, and grounding is very, very important. All of the equipment in your shack should be properly grounded. Now, how do you do that? Well, a really good way to do it is to use, first of all, if you're using a power outlet, you want to make sure you're using the three-prong, grounded power outlets. But also, when you're grounding your gear, a great way to do it is with a chunk of half-inch copper pipe. The kind that you would say get at Home Depot or something like that. And what you want to do is every piece of equipment in your shack, you want to ground it to it. For instance, your transceiver, you want to send it over to it. And they're even showing here, those are those little like clamps that you might see on a radiator hose or something like that. They work great for that. You want to ground that equipment. Your trans match, you want to ground it. If you got a keyer, ground it. If you got an antenna switch, ground it. Long and short, if it's just about anything electrical, you want to make sure that they're connected to a common ground. And you can notice here also that they all go to the bar. You don't want to take the transceiver and then ground it to the trans match and ground it to the keyer and then send it to the bar. You want them all to have an independent ground. And then from there, you want to have a good quality conductor going out to a grounding rod. Again, something that you can pick up at Walmart, Lowe's, or Home Depot. They're typically 6 to 8 feet deep or 8 feet long. And quite literally, you pound them into the ground and you connect your station to them. And what that does is it creates a neutral reference point for all the equipment in your station. Here is just a quick diagram of a three-prong plug in the three-wire electrical line. The black is the hot, the white is referred to the neutral, and the green is the ground. The green is a chassis ground. And in your home, that green line will eventually go to a ground similar to what we talked about over here.
Can I make a comment, Joe?
Please do.
You should always use the green wire ground in addition to the ground rod outside. They have some subtle differences. The green wire ground, its main purpose is like if there's a ground fault to a short circuit to the chassis is called a ground fault. If there's a ground fault, it gives you a return to trip the circuit breaker. And this is a direct connection to tripping the circuit breaker, whereas a ground rod outside your window may have some resistance in that circuit and it might not trip the circuit breaker. The ground rod outside is more for lightning protection or for the radio wave wants a ground to work against, and that references the output of your transmitter to the earth. But so they serve similar functions. But in the electric code, if you have an external ground rod, you got to have that bonded to the main ground by your electric panel. That's part of the electric code. And there's a reason for that also, because if you get a nearby lightning stroke, you can end up with the two grounds at different voltages and mess your equipment up. So yes, use a ground rod outside. That's more for the radiating part. The green wire ground is for safety, but you always connect the electric panel ground to your ground rod. So thank you.
Okay, excellent point there. Thank you, Steve. Okay, I touched on this just a moment ago, but in the United States, again, the black wire in a three-wire 120-volt cable is considered the hot wire. And that is a test question. So remember that. What you want to remember is black is hot. A fuse or circuit breaker should be installed in series with the hot conductor only in a 120-volt AC power circuit. So this is a great point here. If you find yourself, putting in an inline fuse or something like that in any type of an electrical circuit, remember what you want to do is put that in series or put that in line with the hot conductor. The purpose of a fuse in an electrical circuit is to remove power in the event of an overload. Now, fuses are rated, they do have a voltage rating associated with them, but the primary thing that they protect you from is current. Like you've all heard the term probably, a 5 amp fuse, a 10 amp fuse, a 20 amp fuse. What they do is they will blow, they'll self-destruct in a manner of speaking, to prevent too much power or current to go into a circuit. And they're a very important safety measure. So it is unwise to install a 20 amp fuse in place of a 5 amp fuse, as excessive current could cause a fire. Absolutely. If you have a device that is only rated, if you went and checked the fuse on it and it was only designed for a 5 amp fuse, never ever ever put a larger fuse in it. That is a recipe for disaster. It is very unsafe. Now, in a lot of cases, you might be able to get away with putting in a smaller fuse. That wouldn't be unsafe. Now, that fuse may blow on you prematurely, but that would at least be a safe thing to do. So, if you were in a situation where you had a device that ran off of a 5 amp fuse and the only fuse that you could replace it with was a 3 amp, I would make the argument that, well, that is not unsafe, but that device may burn out that 3 amp fuse on you. A hazard might exist in a power supply immediately after turning it off by the charge stored in filter capacitors. We talked about capacitors several weeks ago, and capacitors are devices that resist change in electric potential or resist change in voltage. One way to think about them is they're kind of like temporary batteries. What they do is they hold a charge. So if you have a power supply, and you may have seen this with other types of appliances as well, when you turn them off, sometimes it takes a few seconds for them to completely shut off. You'll see lights dim on them and things like that. And that is because there are capacitors in that device that are still holding a charge. And a capacitor can store a lot of energy. I think, I know it's happened to me before. I'm sure Steve has some stories about it, maybe Bill as well. You got to be very, very careful with capacitors. They can store a lot of voltage, and if you're not careful, working around them, you can get quite a jolt from them. So that is something you want to be aware of, and it may exist for a little while, typically a few seconds after you turn off a power supply. When measuring high voltages with a voltmeter, ensure the voltmeter and leads are rated for use at the voltages being measured. Yeah, you don't want to go and use a voltmeter. Like if you've got a voltmeter that's only supposed to go up to like 5 or 10 volts, don't use that to test the power in your house. The reason being is that you can create, shall we say, a bit of an overload in it. You could damage the meter. So when you're dealing with high voltages, make sure you're using a voltmeter. And this, again, this is kind of one of those common sense type questions. Make sure you're using a voltmeter that's rated for the voltage that you're measuring. Current through the body can cause a health hazard. It may cause injury by heating tissue. It may disrupt the electrical function of cells. It can cause involuntary muscle contractions. Yes, absolutely. All of those things are absolutely true. And I think a little bit later on, they're going to show a little bit of a harrowing picture there of what can happen to you with regards to that. It doesn't make much current, doesn't take a whole lot of current to create a health hazard. As a matter of fact, a quarter of an amp of current can be enough to, electrocute. It could potentially be fatal. So anyway, again, kind of a common sense answer here. Heating of tissue, it can disrupt the electrical function of cells, may cause involuntary muscle contraction. Charging or discharging a battery too quickly is also hazardous. It can cause overheating or outgassing. So that is something you want to be aware of when dealing with batteries. A safety hazard of a 12-volt storage battery is that if the terminals are shorted, it can cause burns, fires, or an explosion. So yeah, especially with the new generation of, there are a lot of batteries that you can get right now that are very, very powerful. As a matter of fact, right here on my desk, I've got a 7 amp hour battery that I use as an emergency backup in my shack. Shorting the leads of that together could be very, very bad. And they show a picture there of what appears to be like a power supply that caught fire and somebody's hand that got perhaps too close to it. But yeah, those are the kind of injuries, second, third degree type burns that could happen with that.
May I say something?
Absolutely.
Notice the ring finger on the hand there. When
Yeah.
you're working on electrical stuff, you always take off your jewelry, because if you short with the gold ring on your finger, it makes the damage that much worse. And as far as the battery, you know, anytime you have stored energy, you have the uncontrolled release of stored energy, you got a problem, whether it's a mousetrap or a chemical reaction in a battery. So that's the basic or a heavy thing up on a shelf with potential energy. The battery has only the internals will limit the current, so that you get a very, very immediate discharge with the chemical reaction. Thank you.
Yeah. Yeah, thank you, Steve. And yeah, excellent point. And also, any type of metal jewelry, if you're working with electronic equipment, if you wear, for instance, a necklace, a cross, a crucifix, even believe it or not, even earrings. If you're working with electrical equipment, and especially if you're going to be sort of getting your head moving around where wires are and things of that sort, absolutely positively want to take those things off. Okay, when putting up an antenna tower, make sure to look for and stay clear of overhead electrical wires. I can't argue with that. That, again, pretty much a common sense question, but be very aware of it. And this is kind of a big deal for me because I actually do have some electrical wires that run out by the backside of my property. Now, here's one that I take a little bit of exception to, but we'll get through this together. When installing an antenna, if it falls, make sure no part of it can come closer than 10 feet to power lines. Okay, that's the magic number you need to know. No more than 10 feet to power lines. My personal feeling is that you want to shoot for 2 or 3 times that much. To me, and this is just Joe McGuire talking, 10 feet for a falling device by a power line is just way too close. But
Just
that is the answer to that.
remember, it'll bounce. That's part of
Yep.
the reason.
Yep. And how are you going to measure that? It's one of those things. You want to make sure that you're very well clear. Okay, your antenna could contact high voltage power lines if it were attached to a utility pole. Again, you may have seen this sticker, by the way, over to the right. This is very common on metal devices and things of that sort. Yeah, absolutely positively, you do not want to mess with utility poles. Do not string antennas to them. I've had to fight off that temptation. Like I said, I've got utility lines that run through the back of my property, and there just happens to be a pole out there, which would be an excellent place for me to string a dipole off of. But I won't do it because that is unsafe. Okay, required when climbing an antenna tower. The problem some people have. Okay, make sure if you ever, if and I wish you all well. If you decide during your ham radio journey that at some point you get yourself a really cool tower with some great antennas on it, good on you. But if you're going to do that, make sure you have sufficient training on safe tower climbing techniques. And you can see the guy over here on the right here, safety glasses, hard hat, harness. The only thing I would probably critique him on was the short sleeve shirt, but I'll kind of let that slide. But you can see there, he's also got one of those riggings that if he accidentally fell off the ladder or if he got a shock, he would not fall to the ground. So have sufficient training on safe tower climbing techniques. Use appropriate tie off to the tower at all times, and that's that clip he's got there, and always wear an approved climbing harness. So all of those answers are correct. Never, ever, ever, it is never safe to climb a tower without a helper or observer. Do not do that. And I want to throw in a caveat to this too, because I actually do this a lot. If you're like me and you do have antennas in your attic, do not go up, especially in the hot months of the summer, into your attic without letting somebody in your household know where you are and what you are doing. Unfortunately, that is also something that has, bit ham radio operators and actually people just doing things in their attic before. It can be very, very dangerous, especially in the hot months of the summer, to be up there. Make sure you've got somebody in your house that knows that you're there and what you were doing, and absolutely positively also bring a cell phone with you. The purpose of a safety wire through a turnbuckle is used to prevent loosening of guy wires from vibration. Yeah, this is turnbuckles like this are used with towers to put the proper tension on them. And the reason that they put safety wires through them, and you can actually kind of see a clip on it there, is to prevent the loosening of the turnbuckle caused by vibrations. And that'll happen, in a windy day like we just had here just last night. Those wires will get rattled around, they'll get shaken, and if they are not properly secured, they will loosen. Okay, practice safety when using a crank-up tower and never climb it unless retracted or the mechanical safety locking devices are installed. There are towers out there that quite literally, just like they described here, you literally crank them up. You can bring them up and take them down using a crank, but they come with a bunch of special safety concerns that you have with it. Do not climb on it unless it is retracted or the mechanical safety locking devices in it are installed. Okay, local electrical codes establish grounding requirements for an amateur radio tower or antenna. That is correct. That's probably all you need to know about this at this time. But I mean, you could hold entire seminars or classes on the proper grounding of towers. There's a lot of techniques. There are a lot of safety standards. There are code standards for towers. So again, in your ham radio journey, if you do get to that point where maybe you're going to have that wonderful opportunity of putting up a tower, make sure you do your homework. Make sure that you are following all the appropriate regulations. There are a bunch of them, and by all means, be safe. Proper grounding for a tower is accomplished by using separate 8-foot long grounding rods for each tower leg bounded to the tower and each other. Yeah, it is something else. I talked earlier about that grounding rod, that 8-foot grounding rod, and you can see here, a little bit tough to see in some parts of this picture, but there are grounding rods on each corner of this, 8 feet long going in there. And you can see they've got grounding straps going out to each one of them. And they're also, of course, grounded to each other. Safety, safety, safety. Okay, bond together all external ground rods or earth connections with heavy wire or a conductive strap. Yeah, you want to make sure you're using high quality, heavy wire for that. Don't go using a very fine wire. For those types of connections, you want to have lots of surface area on the metallic surfaces, and that's why conductive straps are so popular. A good practice with installing ground wires on a tower for lightning protection is to ensure that connections are short and direct. Absolutely. You want to go straight to that ground and make that connection as short as possible. And you really want to avoid, when you're talking lightning protection too, you want to avoid bends in the wire, like right angle bends, if you can at all avoid it. And this is almost sounds like something out of like a Roadrunner coyote type cartoon. Think of that lightning going down the wire and it's screaming down the wire going really fast. Well, long and short, lightning doesn't like to make a turn. And kind of in a manner of speaking, yeah, having that bend in it will present challenges and will diminish the amount of lightning protection you're getting out of the system. Flat copper strap is preferred for RF bonding, and you can see they've got some examples of it there. And yeah, those are just flat pieces of copper. Lots of surface area. That is a real benefit when you're talking about grounding,
Comment?
even than wire. Yeah, go,
comment.
Steve.
As a matter of interest, the same amount of metal, a flat strap will have a lower resistance than a round wire. You can work that out, you calculate it out. But the operative here is the surface area. But that's why flat straps work better than round conductors.
Mhm. Yep, excellent point. Thanks, Steve. Okay, and I talked about this before. Avoid sharp bends on grounding conductors used for lightning protection. Yeah, you want to go straight to it. We showed you that picture of the tower earlier, straight straps going right out to the grounding points. And I hope we're not scaring you with all of this, but a lot of this stuff, especially when you're talking about towers and things like that, that's advanced ham radio stuff. But there are a lot of good techniques you can glean from it that can apply to other stations as well, and it's well worth talking about. Okay, a lightning arrestor in a coaxial feed line gets installed on a ground panel near where the feed lines enter a building. Okay, that is, I don't know if I'm on camera right now, but I have a guest right now. Um, uh, yeah, that lightning arrestor, you want to put that on the coaxial feed line, and that also you want to make sure that that gets grounded as closely as possible. And they do make lightning arrestors, by the way, very popular that will fit right onto your coaxial cable. They've got, Steve mentioned earlier about the PL259 plugs. The socket associated with that is called an SO239 socket, and you can purchase. They're not very expensive. They're good insurance and money well spent. Lightning arresters that have those types of connectors on them, and yeah, you definitely want to get that on your coaxial feed line, right where it enters your building or your home.
May I make a comment?
Sure.
A lightning arrestor will not stop a direct hit.
Hmm.
There's millions of amperes and hundreds of thousands of volts and all of that. But what the lightning arrestor does is it drains off the buildup of static charge, like from blowing wind or from rain. That will build up static charge. Or even if there's a thundercloud overhead, there are some people who subsequently got hit by lightning where the hair was standing up on the back of their neck because they were building up a static charge. Yes.
I was going to, no, I was just saying, Steve, that has happened to me, unfortunately, on a couple of occasions. Occupational hazard.
Oh boy. Uh, and so, but it's not just in thunderstorms also. When there's no thunderstorms around, but like in the wintertime or whatever, and you build up a static charge on your antenna, that can damage the transistors in the output of your transmitter. So you don't want static buildup of any kind because of that. Okay, thank you.
Thanks, Steve. Okay, factors affecting RF exposure of people near an amateur radio station. Okay, RF energy is, depending on the power levels that you're using, things of that sort, is something that you do need to be aware of. And the things that affect RF exposure factors are the frequency and power level of the RF field, the distance of the antenna to the person, and the radiation pattern of the antenna. Now, all of those answers are correct. So, higher frequencies tend to be associated with more hazards. And pretty much anecdotally, I think we could all agree, and this seems to make sense. The more power you're using, of course, the greater amount of energy you'll have in the RF field. So that increases the RF exposure issue. The distance that you are to a person, like here they're depicting an antenna here and some people nearby. Absolutely, the distance that the people are from the antenna is a factor. And then, of course, the radiation pattern of the antenna. And it's very handy that Steve just gave us that lesson on antennas and talked about the radiation pattern. For instance, if we had a Yagi antenna that was highly directional, that place where the greatest amount of radiation coming off of it would be the front portion of it. So, at any rate, all of these answers here are correct. Exposure limits vary with frequency because the human body absorbs more RF energy at some frequencies than at others. 50 megahertz is the frequency that has the lowest value for maximum permissible exposure limit. That's kind of just a number that you want to squirrel away in your brain for the test, 50 megahertz. And by the way, 50 megahertz, if that sounds familiar to you, that is where the 6 meter band is in ham radio. The allowable power density for RF safety change increases by a factor of 2 if the duty cycle changes from 100% to 50%. This is kind of, your RF safety changes increases. In other words, things become more safe. And in this particular case, by a factor of 2, they double if you reduce the power from 100, if the duty cycle reduces from 100% to 50%.
Comment?
That's kind of a little bit of word salad. I'm sorry, Steve, did you have a comment on that?
Yeah, Wesley may not have heard of duty cycle, but duty cycle means how long something is on, what versus how long it's off. So
Mhm.
100% it's on all the time. 50% it's only on half of the time, like on off on off. That's what duty cycle means.
Yep.
Okay, thank you.
So it increases by a factor of 2 if you go from 100% to 50%, which kind of makes sense because, 50% to 100% is doubling or 2. Acceptable methods to determine that your station complies with FCC RF exposure regulations. Okay, there are a few of them. You can use a calculation based on the FCC OET bulletin number 65. And by the way, if you're really curious about that, you can Google that and go find that online. You can do a calculation based on computer modeling, and there are models. If you Google that, there are models out there on the internet for free that you can use for that. And by measurement of field strength using calibrated equipment, there are devices called field strength meters, which will give you a relative indication of how much RF energy is coming off of one of your antennas. Now, again, this is a little bit of more advanced ham radio stuff. For most of the power levels that ham radio operators operate at, this probably isn't too much of a factor. However, remember, and again, as you go off into your ham radio journey, you can use up to 1,500 watts of power. And 1,500 watts of RF power is quite a bit. So when you start to talk especially about more powerful stations and perhaps more directional antennas, these type of things definitely become bigger factors. And you definitely want to take a little bit of time if when you get to a point perhaps where you're using higher power and things of that sort, to spend a little bit of time and learn more about these aspects of RF exposure. But for the purposes of your technician test, that's what you need to know right there. So one way you want to relocate an antenna to prevent exposure to RF radiation in excess of FCC supplied limits. So yeah, if you did all the things that we talked about in the top part of this slide here, and you figured out that your antenna was for lack of better words, a hazard for RF radiation, then one of the things that you might want to do to mitigate that problem is just simply move the antenna. You want to get it away from people or buildings, things of that sort, where people might have, be in closer proximity to it. And radio signals are considered to be non-ionizing types of radiation. And again, that is probably just one of those terms that you want to squirrel away to memory. Radio signals are considered non-ionizing radiation. RF radiation differs from ionizing radiation, which is radioactivity, in that RF radiation does not have sufficient energy to cause chemical changes in cells or damage DNA. That is true, but like we talked about before, when you're talking about higher power levels, there are other hazards associated with it, but it is not like radioactivity, despite the fact that we've got radio in the term. Reevaluate your station whenever an item in the transmitter or antenna system is changed to stay in compliance with RF safety regulations. Absolutely. If you go and, like I mentioned before, if you use a higher power amplifier, if you use a more powerful transmitter, or if you do something to your antenna, if you change your antenna, you should take a moment, think about that, and make sure you're staying in compliance with RF safety regulations. Duty cycle during the averaging time for RF exposure is the percentage of time that the transmitter is transmitting. Steve mentioned this earlier. If something is only on half the time, then its duty cycle is 50%. If it's on continuously, then it's 100%. And that is a key factor in RF exposure. So again, duty cycle, the short answer is duty cycle is the percentage of time that the transmitter is transmitting. Duty cycle is one factor used to determine safe RF radiation exposure levels because it affects the average exposure of people to the radiation. Yeah, duty cycle is pretty much the one thing, because if all other things remain the same, if your proximity to the antenna is the same or the type of antenna that you're using, the radiation pattern, if none of that changes, the thing that's probably going to be the biggest factor is the duty cycle. So here they've got a couple of examples there of how duty cycles can vary. They've got one here where, for instance, a transmitter is only running at a fraction of its power over a certain amount of time. They've got another example here where it's operating for a shorter period of time. And here they're kind of mixing things up a little bit. They've got breaks in where the time intervals are occurring, and then one here where it's operating at a very, very high level of power for a very short period of time. But once again, duty cycle for the purposes of your license exam is measured 0 to 100%, where 100% means it's on all the time and 50% means it's on only half the time. The station licensee is responsible for ensuring no person is exposed to RF energy above the FCC exposure limits. Yep, that's our responsibility as a ham radio to make sure that is the case. Okay, one might receive a painful RF burn if they accidentally touch an antenna while transmitting. Yeah, that's very true. You probably won't find that with things like handheld radios and things of that sort. But then again, if you put your hand on the antenna, you'll be, affecting the performance of it. But again, with shortwave radios, especially when you start to put more power into them, you get up to, shall we say, upwards of 50 to 100 watts or something like that. Yeah, touching that antenna could be a painful RF burn, which is why we always put them outside and we hang them up at very high altitudes, partially for safety, but of course they perform better there as well. And here we've got a few examples of folks working on antennas. These folks here are just doing maintenance. And this guy here went ahead and put his hand on his buddy's mobile radio. Now, mobile radios can have a fair amount of power. You might be talking about 25 or more watts. And you can see here he's getting a little bit of effect from that. His hair's standing up on end. Okay, well, believe it or not, everybody, we have just finished the last section of the last class in our preparation for Cramfest. And on that note, I do want to thank everybody here for hanging in with us. And I'm going to do something a little bit different. We have got about a half an hour left. And, so far, the only questions that we've been working on in the test have been the ones that have been built into the narrative of the instructional portions of the briefings that we're using. But I thought tonight, and especially since we've got about a half an hour left, that we might go through some more questions.